In this video, we continue looking at the solutions to the Chapter 11 problem-solving set where we're focusing on reactions of alcohols. In question 3, we are asked to draw the final major organic product or products resulting from each reaction sequence. So here, what we have are a series of reactions stacked back to back to back, and we're asked what is the final product that would result at the very end of this sequence. In order to tackle problems like this, what I recommend you do is begin by writing out the product that would result from each step. So for example, we could ask, what is step 1 going to yield? When we react alcohol with sulfuric acid, and we have to think back to the reactions that you've learned. Many of these reactions are throwbacks to earlier chapters. And when we have sulfuric acid reacting with an alcohol, we are looking at a dehydration reaction. So the first reaction is an alcohol dehydration reaction, a really common reaction that alcohols undergo. You could think of this as an elimination reaction as well. And in the alcohol dehydration reaction, we do follow Zaitsev's rule, where the alcohol group is going to be the leaving group in this reaction. And what happens is, since we have a relatively strong acid here, the alcohol gets protonated, picks up a proton from the acid. The alcohol leaving group is going to leave. And then at that point, after the alcohol leaving group leaves, the base, water, for example, is going to come in and carry out an elimination reaction by removing a beta proton here, here, or here, at those 3 positions that are beta to our carbon that's bonded to the leaving group. So the carbon bonded to the leaving group is here. That's what we call the alpha position. The beta position is all these adjacent carbons. And so we want to remove a proton at a beta position to enable us to yield the most alkyl substituted product. So what that means is we're going to remove a proton from whatever position here is most alkyl substitute. That's how we're going to yield the most alkyl substituted product. And so removal of a proton either here or here, either way is going to lead to the same Zaitsev's product. Removing a proton out here would not lead to the Zaitsev's product, would lead to a less alkyl substituted product than the maximum alkyl substituted product, which is what Zaitsev's rule says we need to do. So we're going to remove a proton from one of these positions in addition to removing that hydroxy group, and that will create an alkene. And if you need a refresher on this particular reaction, you can find more information about it both in Chapter 11, has dehydration, and also back in our chapter on elimination reactions, Chapter 7, it came up as well. So alcohol dehydration following Zaitsev's rule is what results from the first step of this reaction sequence. Second and third is the reaction series that we recognize from Chapter 8, where we were doing addition reactions across carbon-carbon double bonds. And this was the addition of H and OH across the carbon-carbon double bond that goes opposite Markovnikov's rule. And the name of this reaction sequence was hydroboration oxidation, where the first step with BH3 there was called hydroboration. The second step was the oxidation step with that peroxide. And so what is going to result from this series of reactions, reaction 2 and reaction 3, is that together they will result in the addition of H and OH across the carbon-carbon double bond here. So one of these 2 carbon atoms of the alkene that I'm highlighting here with the laser pointer is going to become CH. The other is going to become COH. And the way that we decide which one of those to put the H on and which to put the OH on is go opposite molecules. So that means that our hydroxy group is going to need to go right here. The hydrogen goes there. So I'll go ahead and plug in that new hydroxy group into this molecule, giving us this. And then finally, down to the home stretch, reaction 4 is another reaction that hopefully we know and love from Chapter 11. This is an oxidizing agent. Anytime you see chromium-6, be thinking oxidation. And so what we're looking to do in oxidation is increase the number of bonds between carbon and oxygen here. Since we have our carbon-oxygen single bond to start with, we'll make that into a double bond. That's a secondary alcohol that we're starting with. Secondary alcohols get oxidized to ketones. So let's go ahead and draw in our final ketone product here, like so. Now, you might also, in this reaction, be asked to provide the configuration of your final product. And that's something that we haven't yet done here, is shown the configuration of the chiral carbon that is right here. So what we need to do in order to determine whether there's a preference for this stereocenter to have the R configuration or the S configuration is think about the pathway of the reaction. So particularly, where do we form the stereocenter in here? So we go from alcohol dehydration, which gave us our alkene, and then from there we add H and OH across the carbon-carbon bond, and we can think about what is the stereochemical outcome of this. So hydroboration oxidation is a sen addition of H and OH. So what that means is that the hydrogen and the hydroxy group add to the same face of the molecules. They're both going to be on wedges, in other words, as I've shown here, or you could also make the enantiomer of this as well. So I'm going to make the enantiomer by leaving everything right where it was, except that the wedges that were pointed toward us now become dashes that point away from us. And so looking at this, going from here, where we have our two sen products, to our final product here, what we're doing during oxidation is only working on this portion of the molecule, converting that carbon-oxygen single bond into a carbon-oxygen double bond. We're not doing anything at the chiral center right here. And so therefore, whatever configuration or configurations existed here at this step will be retained onward to the next step. So you can see here, at this phase of the reaction, we had a dash here and a wedge indicating that both configurations are present. And so therefore, if we're going to plug in the configuration, we need to show a wedge, and we need to also show the dash there. So our two major organic products showing the configuration would be these two ketones. Onward to the next problem. So in the next problem, we are reacting phosphorus tribromide, PBr3, with our alcohol as the first step of this reaction. And what's going to happen in the PBr3 reaction, which you can find the mechanism for this reaction in our chapter 11 material, is that you are going to create a situation where we will set up the reaction for an SN2 type process, where the leaving group will be leaving as a bromide is coming in. And as a result, what's going to happen in this process, this SN2-like process, is that the bromine is going to replace the hydroxy group. And generally, this is going to proceed with inversion of configuration. So, with the bromine replacing the hydroxy group with inversion of configuration, we can draw out the expected product of this reaction. So we need to invert the stereochemistry at that stereocenter there as we replace the hydroxy group with the bromine. And again, strongly recommend you look back at the mechanism for this reaction. That's certainly fair game because it is a mechanism that we went over. And then after that reaction number 1 has taken place, then we go onward to reaction 2, which is specified as an SN1 reaction of methanol with our alkyl halide. So we bring in our CH3OH, and what that is going to do in an SN1 reaction, recall from chapter number 6, that when we have an alkyl halide and a nucleophile, and it's an SN1 reaction, that the leaving group will leave, that's the bromine, will break away to give a carbocation intermediate. The carbocation intermediate could undergo a 1,2 shift, also known as a carbocation rearrangement, if there's one possible. There's not one possible here as a spoiler alert. And then the nucleophile, specifically the oxygen atom from the methanol, will come in, attack the carbocation to get a carbon-oxygen bond forming. Finally, deprotonation will lead us to the final product. You should be very happy to draw out the mechanism for that type of process. We've talked about nucleophilic substitution type reactions a lot this semester, so it's definitely a mechanism that is important. And when thinking about the configuration of the final product here, you might be tempted to do what I just did, which is draw in the dash, much like we've drawn in a dash for the bromine at the chiral center here. But keeping in mind this is an SN1 reaction, you also need to draw the other configuration as well. So I'll go ahead and draw in that other configuration. And the telltale sign, or the way that you can deduce that you do need to draw both the R and S configurations of that stereocenter that you have, is that this was an SN1 reaction. And one of the things we learned way back in chapter 6 about SN1s is that SN1s are not generally particularly stereoselective, which means that you will yield both configurations of that stereocenter that has formed in our product. So here and here we expect to occur as a racemic mixture of the R and the S enantiomer.